Hello, welcome to your lesson on accuracy. Let's define accuracy. A value is accurate if it is close to the exact value of the quantity being measured. So let's say we were trying to measure the number of fish in a pond. If we got a number that is accurate, that means the number we calculated is close to the actual value in the pond. However, in most cases, it is not possible to obtain the exact value of measurement. For example, when measuring your height, you can get more of an accurate measurement if you use a balanced scale that measures to a greater number of decimal places. So we've talked about that in recent lessons about how precise is your measuring tool, how many decimal places can it give you, and all that is part of the same thing here. How accurate can we get when we measure something? Let's jump back to two units of measure that are not part of the metric system, but they are well known. They are the yard and the foot. These are units of length in both the British imperial and the US customary systems of measurement. Metal yard and foot sticks were the original physical standards from which other units of length were derived. In the 19th and 20th centuries, differences in the prototype yards and feet were detected through improved technology, and as a result, in 1959, the lengths of a yard and foot were defined in terms of a meter. So they actually had to define these old kind of measures in terms of this new metric system, which is more precise. So that we know, here's some details. The yard is an English unit of length in both the British and US. We talked about that. Yep, it comprises 3 feet or 36 inches. Since 1959, it is by international agreement standardized as exactly 0.9144 meters. So 4 significant figures, that is what 1 yard is. Okay, a little bit more about SI, because when we talk about SI, it's something that we use more commonly. SI is in 1960 the International System of Units, abbreviated SI by the French, from the French Système International, was adopted as a practical system of units for international use and includes meters for distance, kilograms for mass, and seconds for time. So that's the metric system, and now we can see that right before that 1960 year, the British also tied their yard and foot lengths to this new international standard. Okay, here's a picture of something on a wall somewhere in Britain where it has this metal rod that shows you exactly what 1 British yard is, and then 2 feet, 1 foot, and then some other measures here. So interesting. Like it was said before, there's these metal rods that kind of standardize these lengths. Okay, so a little bit more here. We're going to jump from that and do some experimentation. So in an experiment, students measured a standard yardstick and a foot-long stick. One group used a simple measuring tool. They rounded their measured results to the nearest centimeter, 92 centimeters and 29 centimeters. That's for a yard and a foot. Give all possible unrounded values for each measure. Okay, so it says they rounded their values. And if we know they rounded, then let's assume that they measured to 1 more degree of accuracy. Right here we see rounded to a centimeter. Let's assume they measured to 1/10 of a centimeter. So what would be all the possible values if you have 92 here and you either rounded? Okay, so you rounded to 92. That means we could have rounded up from below 92 or rounded down from above 92. So let's take a look at this one together, and then I'll help you with the next one. And we'll look at 29 as well. So here are the things. This is kind of what this question is asking for. What are the possible unrounded values? Well, again, if we round it to 92, that means we could have had from 91.5, and it says here less than or equal to, because we know when you're equal to 0.5 we round up, so it can be equal to that, and then less than 92.5. So the value they obtained can be any value between 91.5 including 91.5 up to 92.5 but not including it. And likewise for the 29 centimeters that they rounded, that if their tool could measure to 1/10 of a centimeter as well, that means we could be 0.5 below or 0.5 above as well, because they either rounded up from here or rounded down from here and ended up with a 29. So their value, measured value, could have been any value between those values. I hope that makes sense. Let's try that for another situation here. So let's say another group used a more precise measuring tool called a vernier caliper. which can measure to more accuracy. So let's say they rounded their measures to 91.5 centimeters instead of 92 and 31.5 instead of this 29. So now imagine that their tool could measure to one more degree of accuracy. So instead of to one decimal place, they can actually measure to 2, and then they went ahead and rounded. So what would be your statement like this, like we saw above here? What are the possible values like we did here? Can you repeat the same process for this more precise tool? All right, let's check. So in this case, if we rounded to 91.5, that means their tool could have measured to 91.45 or 91.55, and then rounded either up from 45 or down from 55. So again, you assume one more degree of accuracy, and then you can round up or down from there to get what they rounded to. Now let's look at this one here, 31.5. Well, it could have started as 45 and rounded up to 0.5, or 55 and rounded down to 31.5. Again, take a close look at that. This is important that you understand these kind of boundaries of precision. Okay, so here's a question related to that. Can you explain why the intervals in part 1 and part 2 include the endpoint A, so this is like endpoint A, but exclude endpoint B? So again, that means why is this greater than or equal to here, but less than and not equal to here? And you can see it everywhere like that. Okay, so I hope you explained something like this. To be rounded up, the next value can be 5 or higher, whereas it needs to be less than, not equal to 5 in order to be rounded down. So again, you can have this value they measured be equal to 0.45, because that will still be rounded up to 91.5. However, it cannot be equal to 0.55, this value here, because in that case you would round up, so it just means up to that value, but just below it, not including. All right, let's keep going. So what we've been talking about here, establishing this idea of boundaries and lower and upper boundary. This is important in science and that measurement. The left and right ends of an interval in which an exact value of a measurement lies are respectively called the lower bound and the upper bound. So let's go back to the pencil idea we had before. We had this pencil, we measured it here above 14 centimeters, and we had millimeters here as well. So we said the pencil is 14.6 centimeters in length. Okay, and again, we cannot say 14.63 because our tool allows us to measure only up to 14.6 here. Okay, so what are the boundaries? So I did a little zoom in here. Here's a little scale. Here's like the tip of the pencil. Here's 14.5.6. So again, by measuring here, we're saying the pencil is 14.6. But once we surpass these numbers and we get to that last degree of accuracy here, we're in essence estimating our answer here. So 14.6 is what we're saying, but what are the boundaries of what it really could be? So when we set the boundaries, we're going to go above and below that 0.6, and actually we're going to go one more decimal place beyond and then above and below. So the operation is, so you say the degree of accuracy we can get on this ruler is to 0.1, which is a millimeter, right, to 0.1. We divide that by 2, we get 0.05, and now we go above and below 14.6 by that amount. So we set the boundaries by saying, okay, 14.6 minus that, which is one of our units on here divided in half, and it gives us 14.55, and then we say 14.6 plus that amount, and we go up to 14.65. So we're setting the upper and lower boundaries by, again, taking one of our units here, our highest degree of accuracy we can get on the measuring tool, dividing by 2, and going above and below the amount we said. Okay, so that is our range of possible values, because at this point here we're kind of approximating, and that is called our lower bound and our upper bound. You may need to pause for a second, just kind of consider all that. There's a once this idea kind of sticks, it's not difficult, but maybe at first glance it's a little hard to see what's happening here. So consider again what's happening here. We're going above and below and setting the boundaries of measurement accuracy. Okay, so here's some questions related to that. We have Jane's weight is 68 kilograms, and that is measured to the nearest kilogram. So determine the upper and lower bounds of her weight. So remember, when you're doing that, you look at what you're able to measure, which in this case is 68, and then you go to one more decimal place of accuracy and you go above and below by that half and half, right? So what would be our range or our boundaries in this case? All right, check it out. We have boundaries 68.5 and 67.5 for this one here. You can go down half a degree and see it's one more decimal place, up and down. And then in this one, we had somebody's height measured to 155 centimeters. And that says that's all they were able to measure to the nearest centimeter. That's all the accuracy they had. So when we set the boundaries of the accuracy of measurement, we can go 0.5 below and above that as well, like we see here. All right, hope that makes sense. Let's try a few more like that. Here's another. Majid can run or ran 100 meters in 11.3 seconds. His time is measured to the nearest tenth of a second. So they had some very precise tool measuring that time. 11.3 seconds exactly. So now determine the upper and lower bounds of that time. Because again, our measuring tool, that final degree of precision can then be said to be an estimate. So therefore you go a little bit further to show the boundaries. So what would it be in this case? Okay, in this case, it went to 1 decimal place of accuracy on our tool. So we go 1 further decimal place, which we can see here is 0.05, and we divide by 2. Went below and above. So here are our boundaries. 11.25 is below that, 11.35 above that. There's our boundaries of measurement. All right, try this one out. And I'll let you know with this one, might seem a little different than you might think at first. It says a garden plot has these measurements, length and width, and it says figure out the lower and upper boundaries of its, or bounds of its perimeter. Okay, in this one, I would suggest you look at the length and the width separately. Do not calculate the whole perimeter and then set the bounds. Look at the length and width separately, set the bounds on them separately, and then proceed from there. See what happens. All right, in this case, see, they set the boundaries for length by going 0.5 below, 0.5 above, and they set the boundaries here for width, also going 0.5 below, 0.5 above. And therefore, our perimeter, we know, is 2 times those combined, because when you combine the length and width, you have 2 sides of a rectangle, and then you just double that to get all 4 sides. So our perimeter is just double that. So 470 when we use the lower boundaries, and 474 when we use the upper boundaries. So then when we set the boundaries for perimeter, we have the lower and upper based on these. Take a look at that closely. Okay, so now we're moving on to something called measurement error. As we've been showing, when we use a measuring tool, the final degree or decimal place of precision we get is an approximation, the final one, right? So that implies that we have these boundaries, right? We've created these boundaries, the lower and upper boundaries, and we know our exact value somewhere in between those. And that fact that our exact value is between a range of numbers means there's some error inherent in what we've done in our measurement. So that is called measurement error. Measurement error, and let me read this out then. So since measurements are approximate, there's always error in the measurement results. A measurement error is the difference between the exact value, we're going to call it this, and the approximate value, this. To find the error, you do here the approximate value minus the exact value. Okay, so let's look at that through an example. We have 2 people, Tommy and Massimo, who measured the length of the yardstick and the length of a foot-long string and obtained these measures, 92.44 centimeters for the yard and 31.48 centimeters for the foot. Okay, the exact values are 91.44 for a yard, so you can see theirs is different than that, and 1 foot is this compared to what they measured here. So find the measurement error. So use this little formula to find the measurement error for the yard and the foot. So just use that formula with the values you have here. Let's see what you get. So the yard error they made, okay, here's what they got minus the exact value, and that gives us an error of 1. They're off by one actually in their thing. That's their error. How about for the foot? For the foot, this is what they got. This is the actual subtract, and it's off by 1 as well. So in both cases, their error is 1. Okay, or 1 foot, they were off by 1 centimeter in both cases. So, follow-up question. Tommy thinks the 2 measurements were equally inaccurate. Okay, he says, well, we were off by 1 centimeter here and 1 centimeter here, therefore we were equally inaccurate. Massimo, however, thinks that one of the 2 measurements is more accurate than the other. Who do you agree with? What do you think? Explain. Okay, so I wonder what you answered, but let's talk about it. First of all, it is wrong to say that there's the same level of inaccuracy here. Yes, they are both off by 1 centimeter, but 1 centimeter off of the real amount here is a much smaller part of this amount than 1 centimeter here, right? Like 1 centimeter out of 91 centimeters is a smaller proportion than 1 centimeter out of 30 centimeters. So this is greater inaccuracy here. And the way we measure that is through another formula that combines measurement error with percentages. That is called the percent error formula. Looks like this. Definitely write this one down. That's one of the key formulas of our opening units here. So you can see the measurement error that we just did right here. But in this case, we take the measurement error and we divide by the exact value. And that basically says, well, we have the error, but what portion of the whole value is the error? And that division there basically tells us what portion of the error is. Is it a small portion or a big portion of the exact value? Let's see how it works. So here's the yard error. Use this percentage error formula to figure out what percent error this is of this. So just plug in the values. These two here, by the way, mean absolute value. So if you obtain a negative value in that calculation, you just make it positive. And at the end, we multiply by 100% to turn this into a percent. So let's see what you get for this one. Okay, so here are those values into the percent error formula. And when you calculate it, again, we already knew that the top is going to be our 1 because that matches what we did here. There's our error. And how big is it as part of the exact value, or 1 out of 91, right? The 1 out of that will tell us what percent it is. So multiply, it's only 1.09%. That 1 represents only about 1% or a little bit more than 1% of that. So that's a small error that they made when they measured that. How about when they measured how about when they measured the foot? They're also off by 1 centimeter. But as a percentage error, let's see what that works out to. Let's check your work. So again, we're doing the subtraction here, which we already did here. So we know this is going to be 1 on top. So there's the 1. And now we're saying 1 centimeter out of the exact value. And you can see here, 1 out of 91 is smaller than 1 out of 30. So this is going to be a bigger percentage error. Let's see what we get. That works out to 3.28%. Makes sense. Again, 1 out of 30 is a bigger proportion than 1 out of 91, and that's what the percentage error formula tells us. It tells us how big our error was in relation to the actual values. So more error here. Okay, try one more like this. We know that the fraction 22/7 is often used as an approximation of pi, and we know pi is this decimal. It's an irrational number, a decimal that goes on forever with no pattern or repetition. So is this a good approximation? How many decimal places does this approximate pi? Well, you might want to use the formula we just learned and try to put in pi and all that and see how close we are. Okay, here's an answer for A. So the approach that they took here, which is a good one here, where you take that fraction, that's the approximation, minus pi, and you figure out how far off you are. So that's our error, right? That's our measurement error. And you can see 0, 0, 0. That means that those numbers they match. If you did 22/7, you would get 3.14 and then some other numbers. And we know pi begins with 3.14. So that's why these become 0, because this approximation matches those 3 digits. But after that, it doesn't match. That's why there's a difference here when you subtract. So this is a good approximation to 2 decimal places. We can see 0, 0, those 2 canceled. 3.14 canceled. So it's good to 2 decimal places. Okay, so now find the percentage error. Okay, percentage error formula, plugging all that into that formula, and we're off by 0.04%. So this fraction is a pretty good approximation of pi. It's not even a 1% error. Very, very good approximation. Okay, last question here. We have, it says calculate the density of a cube of sugar weighing 2.45 grams, where the side of the cube is 1.2 centimeters correct to 1 decimal place. Use a volume value correct to 4 significant figures when finding the density. Okay, let me explain that. So first of all, here's a cube, and you should know when you find the volume of a cube, all the sides are the same, and all you do is side times side times side. It's like length times width times height, which means side cubed. That will find you the volume. And then you can use this formula to find density. Density is found by doing the mass divided by the volume. You have all the numbers you need here, and remember, when you're using this formula and you're using the volume, make sure you put a volume correct to 4 significant figures down here when you're calculating it. Let's try. Okay, so here's the volume. 1.2 cubed was the size of the cube. here's volume to 4 significant figures like I requested here. Then you put it in the density formula with the mass on top and that volume on the bottom, and you get this. So that is your density, okay, like this. Now, follow-up question. Find the percentage error that would occur for the density. Okay, so if you calculated this density, if you had rounded both mass and volume to 1 decimal place. So let's say you had rounded this to 1 decimal and this to 1 decimal, you would get a different density. And how different would that be from what you have here? Find the percentage error. Okay, so we're using percent error formula again, but we begin by, again, rounding our mass, rounding our volume, like it said here, to 1 decimal place, getting a new value here, and then calculating that rounding as well, and then seeing what the percentage error is here. Okay, so that one just kind of illustrates that rounding changes things a lot. So avoid rounding when you're solving problems. Keep as many significant figures as you can, and do only a final rounding at the end, because rounding really changes the results along the way. We can see 5.8% difference here. That's a big difference. Great job. We'll see you soon.